Oxidation numbers are next. In my opinion, this is the second most important concept as it relates to the redox unit. We can use oxidation numbers in a lot of different ways, and it helps us to identify those terms we talked about in our previous lesson, which was reducing agents, oxidizing agents, reduction, and oxidation. And I'll show you how that works today. The first thing that you need to understand is that oxidation numbers is just a systematic way of counting electrons. And because it's just a systematic way of counting electrons, when we are assigning oxidation numbers, we assign them in compounds so that the sum of all those oxidation numbers equals the charge of that compound or ion. So, for example, if I've got a compound that has a neutral charge, then the sum of all the oxidation numbers is going to equal 0. If I have a compound that has a charge on it, so an ion, either a simple ion or a complex ion, then the oxidation numbers, the sum of them, will need to equal the charge on that ion. The next thing is that you need to understand that oxidation numbers are not charges. We use the charges to help us assign oxidation numbers in lots of instances, as I just explained, but oxidation numbers are not the charge. You'll find that in some cases, the oxidation number will change for a particular atom depending on what compound it's in. And so you have to understand that oxidation numbers are different than charges themselves, but we do use the charges in certain scenarios in order to help us assign those oxidation numbers. The oxidation numbers, remember, this is the most key and important concept as it relates to understanding oxidation numbers, is that they're just a systematic way of counting the transfer of electrons for a redox reaction, which is just that. A redox reaction is a transfer of electrons from one substance to another. So here's some rules for assigning oxidation numbers. The first is that elements, anytime they're in their elemental form or elements by themselves, their oxidation number is going to be 0. The next is simple ions, and their oxidation number is just going to be their charge. So that's a case where you can see that the oxidation number is the same as their charge. They are two different things though. Number 3, oxygen in a compound. When I find oxygen in a compound, it's going to have an oxidation number of -2. There's one exception to this, and that's when we find oxygen in a peroxide compound. So for example, hydrogen peroxide, oxygen is going to have an oxidation number of -1. And the last rule is hydrogen in a compound is going to be +1. Again, one more exception to this, and it's when I find hydrogen in a hydride compound, hydrogen in that compound is going to have an oxidation number of -1. So here's a couple of examples showing you how to assign oxidation numbers. First of all, this one right here, P4, that's an element. Phosphorus by itself is P4, that's in its elemental form, and so the oxidation number for P4 is just 0. And the way that I'm going to do that is I'm just going to write the 0 just above the element to show what the oxidation number is. This is magnesium. Again, it's in its elemental form, it has no charge, and its oxidation number is going to follow then this rule, which is it's an element, its oxidation number is 0. The third one is aluminum, Al3 positive. This has an oxidation number that's equal to its charge, so 3 positive. So that's how I do this, okay? Moving on to a couple more complex examples where these are now compounds. Remember, as I said before, that the oxidation number, the sum of them has to equal the charge on the compound. So this is a neutral compound, so the sum of all these oxidation numbers have to equal 0. And this one is nice because this is, as you can see, an ionic compound. And ionic compounds are simply just made of ions, right? This is made of a beryllium ion and a sulfide ion. Now, if you look in your periodic table, beryllium has a charge of 2 positive, and sulfur has a charge of 2 negative. And because these are simple ions, it can follow this second rule here, which is simple ions have an oxidation number of just their charge. So the beryllium atom here is going to have a +2, and the sulfide ion is going to have a -2. And so if you add these up together, again, you can see that 2 positive plus 2 negative gives me 0, and that works out. Okay? For methane here, I've got hydrogen in a compound, so that's going to give me this rule number 4 here, where hydrogen has to be a +1. I know that this whole compound has to equal 0 because it's a compound that has no charge. And just with some simple algebra here, I can solve for what the oxidation number is for carbon. Carbon doesn't really fit into any one of these rules right here, so mathematically I have to now calculate this. So you can see I've got 4 hydrogens in this compound, and each hydrogen has a +1 for an oxidation number. So I have to add all of those together. So 4 times +1 is there. Now, some number for carbon plus a +4 has to equal 0 for this. And so I do some quick algebra and I can figure this out quite easily, that carbon is going to be a -4 for that compound. Moving on to the next one, sometimes you can get compounds that do have charges on them. So if they have charges, again, it's got to equal the sum of the charge on the compound. So this is not going to equal 0 this time, this is going to equal a -1. And I know that oxygen is in a compound, so it's going to have an oxidation number of -2. This is 4 times a -2, which gives me a total of -8 altogether. And again, I know that something plus a -8 has to equal a -1. And so manganese here is going to be a +7. Moving on to the next one, Fe2 So4 3. Again, this one is an ionic compound, and so the first thing that you want to do when you come across ionic compounds is just split them up into their ions, because that's what they're made of. This compound here is made of Fe 3+ and SO4 2-. And so Fe 3+ is a simple ion. Its oxidation number is going to be its charge, so just 3+. And that one's done. Now I can assign the oxidation numbers to that complex ion, SO4 2-. And I know that oxygen again is a -2. This whole thing is going to equal a -2. And so I go 2 times 4 is a -8 altogether, which means that this must be a +6 plus a -8 gives me a -2. That means that sulfur here is just going to be the +6. And then the last thing that you can do here is you can assign oxidation numbers to substances in chemical reactions, and that will help you understand where the electron transfer has happened. So if I look at example number 8 here, this is a good example of a redox reaction where I can identify now what's being reduced and what's being oxidized. Just make a little bit of space here. So again, this one, methane, this is going to be a +1, and this is going to be a -4. The oxygen, O2, is an element, so that's oxidation. That oxidation number is going to be a 0. Carbon dioxide is a compound, so oxygen's a -2. And write that a little bigger. And the carbon in CO2 is going to be a +4 in this case. And then H2O, oxygen is a -2, and hydrogen in a compound is +1, and so I can assign that like that. And you can check my work here and make sure that the sum of the oxidation numbers in each individual compound equals the charge of that compound, and you can see there that it does. So now what I can do is I can compare how oxidation numbers have changed for particular elements, and that will help me identify what is the oxidizing agent and what is the reducing agent. So if I look at carbon here, I can see that carbon has changed from a -4 to a +4. So in order for something to become more positive, in chemistry we know that we're just talking about transfer of electrons. So when electrons are moving from one thing to another, if I lose electrons, I become more positive. If I gain electrons, I become more negative. And in this case, carbon, you can see, becomes more positive in this case. And so that means that CH4 lost electrons. And if CH4 lost electrons, then that means that CH4 was oxidized. And if CH4 was oxidized, then that means that it's the reducing agent. Conversely, if you look at oxygen, oxygen went from 0 to a -2 on the product side. In both instances, you can see it was split up, and that's fine. In either case, we see that oxygen, its oxidation number went down, or in other words, was reduced, became smaller. And that's where this term comes from. Reduction is that the oxidation number of a particular substance has become smaller or been reduced. And so this gained electrons because it became more negative, which means that it was reduced, which means it is my oxidizing agent. So that's how I can use oxidation numbers to determine things that are being reduced, things that are being oxidized, and identify what's my oxidizing agent and my reducing agent.